so that we know, is there a threat out there that we're facing that we do not yet know about?
Wow, I mean, it's incredible just to know the work that is already being done. It's good to know that we're building off of it, but it's good to know we've already got some people watching the skies. Yeah. And so I have our next question from Alan on Twitter, who asks, how long does it take for pictures to reach Earth? Kelly.
Well, the time it takes light and then a radio signal from the spacecraft to come to Earth is 38 seconds. But then there's also the time needed to process the images, so a few more seconds on top of that. So under a minute, but still it's not instantaneous because it's a ways out there.
Well, that makes sense. I mean, but under a minute to get something back from space, I'd say we're doing pretty good right there. That's right. So, Lucas, Kelly, thank you so much for everything that y'all are doing to keep our planet safe.
Thanks, Hera.
And so it's important to note that tonight we're attempting something that's never been done. And with that presents many challenges to overcome. Here's what makes DART a first-of-its-kind mission.
The DART mission is a very difficult mission because we are trying to do something that hasn't been done before.
This is the first time we're going to an asteroid that is this small, this dark, and we're actually going to attempt an impact.
The DART mission is really something that the whole world can get behind.
We're doing this mission to prove that we can deflect an asteroid if we find one that is on an impact course for Earth.
We are trying to hit an asteroid 163 meters wide, which is about the size of the Washington Monument, while flying at 6 kilometers per second, which is like going from New York to DC in about a minute.
There is no chance that this asteroid could ever hit Earth.
It's a very small asteroid. It's only about the size of a small football stadium, and it's almost 7 million miles away from the Earth. That's 28 times the distance between the Earth and the Moon.
There's kind of a limit on how much mass you can launch into space. You know, rockets are only so big. So our spacecraft is only the size of a golf cart.
Draco is the primary instrument on the DART spacecraft. It is the camera that is going to be imaging the Didymos system as we approach.
When we first see the asteroid through Draco, it's just going to look like a pixel.
There's a star tracker on board that takes images of the stars and compares them to a known catalog to determine which way it's pointing in space. It poses the biggest risk because very, very small errors in this measurement can spell the difference between success and failure. And those measurements are going to be fed into the SmartNav algorithm that's going to be making the autonomous course correction commands that will put us on an intercept course.
There is a very small probability that we don't hit the asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, we are looking, we're finding the asteroid, even then, we might still miss.
We're trying to teach a computer how to recognize an object we've never seen before.
And the way it does that is by taking pictures of the asteroid and then interpreting where it is in space and guiding itself to it.
The spacecraft is controlling itself. SmartNav is guiding the spacecraft. And we have very limited ability to respond in that time. So it has to do it all by itself.
And at about 2.5 minutes out, we cease all maneuvering and we coast until we hit the asteroid.
It is going very, very fast towards the asteroid, traveling at 6 kilometers per second.
200 times faster than a car on the freeway. So when we hit, all of that mass, all of that momentum pushes the asteroid.
Even giving it a small nudge will allow it to change its course.
But if we did see an asteroid on track for Earth, this would be enough of a deflection.
It's like a bittersweet moment. Yeah, all this hard work just got destroyed, but that was exactly why we put it all together.
Of all the endeavors that we do for space and in space, this is probably one of the ones that one day will be the most important thing that we've ever done.
In the future, I hope that DART can teach us what ways work and what ways don't work for planetary defense. Because
it is humankind's first demonstration that we have gained the knowledge and the technology to be able to protect the Earth from an asteroid impact.
Space exploration is rooted in pushing past boundaries. Remember, tonight is a test, and we hope to make impact. Now that you've learned of the challenges today's test, let's head back to mission operations and get a status update on DART's real-time progress. Samson, how are we looking?
Hey, Hera, we have 30 minutes to go until impact. As we heard earlier, so far so good. SmartNav is now targeting Dimorphos, thrusters are firing, maneuvering the spacecraft. Draco, DART's eye, playing paparazzi with Dimorphos, providing SmartNav with about an image per second. And this is a good time to remind you that what we're seeing on the Draco feed is delayed by about 45 seconds on account of signal delay and image processing. And coming up, we're about to see the team conduct a final poll, one last scheduled confab to make sure that all systems are go. And as we head to that, I have someone with me who knows a thing or two about ensuring spacecraft readiness and integrity. Betsy Congdon, DART's mechanical systems engineer. Betsy, thank you so much for joining me.
Thank you.
So you led the team that literally put DART together, is that right, Betsy?
Yeah, so my job is to make sure the engineers and the technicians all physically put all these boxes that you've been hearing, bolts and all onto a spacecraft altogether.
I got to ask, with a mission so ambitious, how many hours, how many years, how many people? Do you have any idea at this point?
Oh, man. So, I mean, DART has been thought about for a long time, but really started in earnest about 5 years ago. We started building up the spacecraft and, in that assembly that I was talking about 2.5 years ago. And so it's been hundreds of hours, to make something like this possible. People with all sorts of talents. You've seen a lot of them today.
That's incredible. And so we're heading up toward another status update, as I said earlier. And as we all know, space is a unique and challenging environment. When you're assembling DART, what were the key boxes you were checking off of that very long quality assurance list to get the spacecraft to where it is right now and hopefully till impact?
So space is very hard, and so what we do is each individual component, Lisa was talking about this earlier, goes through its own individual testing, and then we put the whole spacecraft together, and we will check out the electrical systems, making sure all the boxes are working and talking to each other. We put it into a vacuum chamber, make sure it's going to work in space, put it through all the different temperatures it's going to see, and then put it on a shaker table and actually mimic launch. And so it actually goes through all of that as a full spacecraft as well as individual components. So we go through a lot of testing, mission operations, mission simulations to get to this point.
That's incredible. I mean, I don't know if you included, you mentioned so much array. Is that also accounting for the temperature fluctuations in space? That's another key part.
Yeah, so we have chambers here at APL that are specially built to take these spacecraft, put them into the vacuum of space, and run them through the temperature spaces that we're going to actually see.
It's incredible. How many times do you check? Is it like one test and we're done, or are you sometimes testing and testing?
Lots and lots of testing, and that's what makes it, so perfect. We're seeing these great images coming in because of all that testing and all of that work. So, you don't do anything once. You're doing it many times because once it's in space, there's not a lot of ways to fix it.
Right. Well, do you ever, think about that one panel, that one component that gave you a little bit of heartburn in the clean room, and you're up at night thinking, I think that thing is going to hold true up until the end?
Everything is looking really good. I will say, we had a lot of new technologies, which are really exciting. The ROSA solar arrays had never been integrated onto a spacecraft before, and so that was like a challenge, but one the team was up for, and now it's all ready and working perfectly.
All these new technology demonstrations, it only adds to the complexity of this mission and to, testing things. I wouldn't say even more so, but it's just as critical. But new technology, everything has to be so to make sure it comes.
Yeah, all of this new technology just requires extra testing, but that just gains confidence. You're seeing the team working through that, working through all these mission sims. So that's really what makes it exciting. You don't want to just do the same thing over and over. This is what makes APL a special place. We build these special spacecraft that, have never been done before.
Last quick question for you. It's got to be a little bittersweet that a spacecraft you poured heart and soul into is about to careen into an asteroid. How are you feeling about that?
I'm feeling great about it. It was designed to careen into the asteroid. It's meeting its destiny. So it's really exciting to see, and I can't wait for impact.
Well, it is serving a purpose. I guess that's why it's easier to let it go. Right?
Exactly, very much so.
That is awesome. Well, I think we are about to get into that final poll in the mock very shortly. So we're going to hear that final 30-minute poll, and then we're going to hear from Lena Adams again, DART's mission systems engineer, to give us that summary of what we just heard, how she's feeling, how they're feeling in there. Very exciting stuff. This will be the final poll of the evening. We are awaiting that final poll.
This is DART MSC on DT Mach. It is time for the last status poll. Yes. We're about, 7,000 miles from Dimorphos at this point, so yay. All right, image quality. How are we doing?
Still looking very good. Dimorphos still tracking along that same brightness predict as Didymos.
That's great. All right.
Maneuver complete.
Yes, thank you. All right. SmartNav.
SmartNav is looking nominal. We're at under 30 meters of projected miss distance right now.
Yeah, it's looking really good. Look at that. That's looking fantastic. Very excited. All right, GNC.
Yeah, GNC also looking good. We've been very excited to do those burns, so we've been waiting a long time.
Oh, this is great. Autonomy.
Autonomy is green. The heaters are cycling nominally, and we've had no new fault rules firing.
Okay, wonderful. DSN.
DSN is green, and ESA is green. Got plenty of margin. Looks good.
All right, ground systems.
Ground system has been helping a few users manage clients, but everything is going fine there, and we are green.
Yes, wonderful. Thank you, guys. Completes the poll. Last one. All right, so Didymos is looking like itself. We'll see what Dimorphos is looking like soon. In the meantime, we're going to transition to precision lock at 20 minutes. That's our next milestone. So thanks all.
All right, we're about to hear from Lena Adams from the Mission Operations Center.
Hi, Samson.
Hi, Lena. That sounded very positive. How's it going in there?
Oh, it's going great. It's going great. We've locked on Dimorphos. We're maneuvering towards it, and yeah, everything is looking really good. We were at the time of the poll within just a few meters of projected miss distance, which means we were hitting towards the center. And at this point, we're coming back there about 30 meters off the center of the lit portion of Dimorphos as of right now. We've executed 2 burns. And everything's looking on track.
Oh, that sounds wonderful, Lena. Thanks so much for that, and good luck on the final stretch.
Thank you. Have a good one.
All right, Betsy. We had that very positive poll, lots of fantastics, lots of clapping. We heard Lena in a very positive mood. How are you feeling?
I'm feeling great. It's amazing to see the actual dots on the screen for real coming down from the spacecraft.
Very exciting. Any words of encouragement for the team?
I mean, obviously, they're doing a great job. They've practiced a ton, and we're ready. Go DART.
You've heard it all loud and clear to Hera. All systems are go, and we remain on track for impact. And like Betsy just said, go DART. Back to you.
All right. What an exciting update, Samson. You just heard it. All systems are go. Mission operations confirm the spacecraft is on track for impact. But in order to hit the mark, the test must first locate its target. That's why Johns Hopkins APL engineer Michelle Chen helped develop new autonomous navigation techniques that will ensure a bullseye. Let's take a look.
Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen, and I lead the team that is responsible for the autonomous navigation of DART spacecraft to hit an asteroid. The DART mission is the first planetary defense test mission. Our goal is to hit and impact an asteroid to understand and study the momentum transfer so that we could potentially later down the road, if we need to, deflect an asteroid on its way to Earth. I am the SmartNav lead. SmartNav stands for Small Body Maneuvering, Autonomous Real-Time Navigation. SmartNav, I always consider it sort of like the brains, And so the camera, Draco, is essentially the eyes. The algorithm has to identify and hit the target in the field of view of the camera. We're flying at over 6 kilometers a second. It essentially occupies a pixel up until possibly 30 minutes prior to impact, and then that's where everything gets really exciting. And so you could just imagine if it was a human being joysticking this. Because we don't know for sure what the asteroids look like, our simulation gives us the capability to use different asteroid shapes and asteroid objects to see that our SmartNav algorithm performs against all these unknowns. We're super excited and nervous as well. I love pushing the boundaries, and I love the application of math into real-world problems, and then seeing it actually doing its thing. To me, there's nothing cooler than that.
If you're just joining us, we're about 24 minutes away from DART's impact with asteroid Dimorphos. The spacecraft is flying at 4 miles per second, guided only by its autonomous navigation system. I'm here now with Tom Statler, DART program scientist, and Don Graninger, DART impact modeler. Tom, Don, thank you for being here with us tonight. We have some good news happening, but we did just hear about the challenges that DART is facing tonight. So, Don, could you tell us a little bit about what kind of uncertainty exists with a mission like this?
Yeah, sure. So what's really interesting is that until just, even a few minutes ago, I feel like we're just getting our first looks at Dimorphos. And so we have absolutely no idea what we're going to be impacting into. It could be covered in rubble pile. It could be just a completely different shape. We don't know until we really write up on that impact. And that's probably one of our biggest uncertainties on this.
I mean, but that's what really makes tonight so exciting. And so, Tom, could you expand a little bit more on how we will use this information in the future if all goes successfully?
Well, this test is really important to understand how we might be able to deflect asteroids in the future. And when we measure the change in the binary period of Dimorphos, and we will understand how the asteroid reacted to our kinetic impact. And then as we get deeper understanding into exactly what the geology was of that asteroid, that's the basic information that's going to help us refine our physics understanding of asteroids and our ability to compute and predict, like Don does, run these fantastic codes and extend this knowledge to really have a good plan for how we might react if we ever do discover a dangerous asteroid that is different from Dimorphos.
Well, hey, I mean, it's better to be safe than sorry. So it sounds like y'all's party is really just getting started after impact. So congratulations on your success so far. It has been a pleasure. Thank you so much. Now, any second, we should be learning if DART has a precision lock on its target Dimorphos. This is a key milestone critical to tonight's success. Samson, mission operations must be buzzing. How are things going?
Hey, Hera. The energy is indeed electric, and the team is hyper-focused. You could hear a pin drop right now as we're coming up on the critical 20-minute mark from impact and expecting to hear from the team that SmartNav is now precision-locked onto Dimorphos, which means that SmartNav will be tracking only Dimorphos from here on out. Why? SmartNav has full confidence that we're in fact tracking Dimorphos, and so we want to remove any confusion by continuing to track Didymos. Because what could happen with Didymos is that its shape could be such that there's a lot of shadowing, which could make it seem in the Draco imagery like multiple blobs, as the team likes to call them. And we don't want SmartNav to mistake any of those blobs for Dimorphos, so we're doing away with tracking Didymos altogether. We are waiting for that announcement of precision lock. All right, we're about to hear from the team. Actually, we have some time until we hear that. And now let's listen in for that confirmation of precision lock.
All right, we expect to be in precision lock soon.
We are waiting for confirmation of precision lock.
MSC, this is SN5.
Go ahead, SN5.
We are precision locked and still tracking Dimorphos.
Yes.
We are soon going to hear again from Elena Adams.
This is great. This is DART MSC on DT Mach. So this was our last milestone. At this point, we're going to be working towards Dimorphos. I expect we're going to do some burns. We're about 4,500 miles away from Didymos and Dimorphos. So let's see what happens.
Groundstar 41, FC2.
Right, joining me now to react to that bit of good news is Lindley Johnson, NASA's Planetary Defense Officer. Lindley, you heard Lena, we are now precision locked, a lot of applause, things are looking good. And we are now headed for the moment of truth. How are you holding up?
Oh, I'm doing great. The team's been doing great. The spacecraft's doing great. It's this precision lock, is absolute milestone for the terminal phase here. We've got a good signature on Dimorphos, so the spacecraft has what it needs to guide itself in for the impact here in 17, almost 18 minutes. So we're doing great.
Yep, so close. Very exciting moments ahead. Now, we can't say this enough, and I know you've said it so many times, but it's worth repeating for viewers that Dimorphos is not a threat to Earth, nor will it be after impact, right?
No, that's right. This asteroid system is still almost 7 million miles away from the Earth. It's at its closest point in the orbit right now to Earth. So from this point forward, it's going to be moving away from Earth. So there's no chance of anything here. We've got to look for all the other unknown asteroids out there still to find what the hazard really is.
Thanks so much, Lindley. I'll catch you on the other side of impact.
Okay, if you can.
Back to you, Hera.
All right, thanks, Samson. It is amazing to know that we have a precision lock on target Dimorphos. Now, we have a fun way for you to join our mission, and it is by signing up to be a planetary defender. Visit bity.com/planetary defender. Take the quiz and receive a certificate like this one. Now, once it's official, show us on social media using the hashtag Planetary Defender. Now, telescopes from around the world are observing tonight's impact to ensure that how successful we are at changing the asteroid's orbit. They'll be measuring this success. And you may be wondering, how does that happen? Let's go behind the scenes with astronomer Nick Moskovitz at Lowell Observatory, home to the telescope that discovered Pluto, to see what's in store for DART.
This is Lowell Observatory. Lowell is one of many observatories around the world that will be observing the DART impact, NASA's first ever planetary defense test mission, to see how much a spacecraft impact can deflect an asteroid in its orbit. This is where Pluto was discovered, and we are still doing research in all areas of astronomy today. So let's go check it out. This is the Pluto telescope, the telescope that was used to discover Pluto almost 100 years ago. So here we are at the Clark Telescope. This is where Percival Lowell sat to observe Mars. Let's head on over to the Lowell Discovery Telescope about an hour south of Flagstaff, which is where we are going to be collecting data for the DART mission. And the reason we're all the way out here in the middle of this forest is that we have really dark skies here. And this is the Lowell Discovery Telescope. This is what a 4.3 meter telescope looks like. This is what we will be using to study Didymos and Dimorphos in the days and weeks after DART impact. The DART spacecraft will be hitting an asteroid called Dimorphos. It's special because it's a binary asteroid, which means a satellite around a larger asteroid called Didymos. And DART will actually be hitting Dimorphos And what we will be measuring is how much DART changes the orbit of Dimorphos around Didymos. So this is an important test for planetary defense mitigation strategies in case we ever have to do this for real. The Lowell Discovery Telescope is one of many telescopes around the world which will be used to study Didymos and Dimorphos. It's really a global coordinated effort. And what we're looking at here is a large 4.3 meter primary mirror that's in the middle of the telescope tube here. Up at the top is a secondary mirror. The secondary mirror up top there is what is focusing the light down onto the instruments and allows us to take images with the camera that's located down at the bottom. This is maybe one of my favorite hidden rooms at the telescope. We're like standing inside the telescope, underneath the telescope, 100 tons above your head, held up by this and this, which is cool. It's sort of, as you can see, the highest peak around here, just over 8,000 feet. I come up here for sunset. It's, sun setting right there. It's perfect. For DART, we're going to be collecting images of the night sky. And typically an observer would be here in front of one of these consoles controlling the instrument and taking images like these as they're coming in off the telescope. DART is really a sort of before and after experiment. We need to understand the system before the spacecraft intentionally impacts, and then we have to understand what the outcome of that impact event is. As we watch from the Earth, Dimorphos will pass in front of Didymos and behind Didymos. What we will be doing with those images is measuring the brightness of Didymos in those images and looking at how that brightness changes. And those dips in brightness allow us to measure when these eclipses happen and measure the orbit period of Dimorphos. And so you have essentially a fixed star field here. All the white dots are stars of different brightness, and moving through this field is Didymos and Dimorphos, which again, we can't distinguish them as discrete points of light, but we have that small object moving through the field of view. So after impact, we will then be able to go back and start observing intensely, looking for those mutual events, those eclipse events of Dimorphos passing in front of and behind Didymos. And on each one of these frames, we're measuring the brightness to assess whether or not it's undergoing one of these events where Dimorphos is passing in front of or behind, and using those to determine the orbit period of Dimorphos around Didymos. This is such a cool experiment. It's such a singular experiment. Using the ground-based telescopes like this one and others around the world to watch the system and see how it's affected by this impact event, because that's really what's going to give us the answer to what did DART do at the time of impact. And that will be exciting to see how that evolves over the days and weeks following that impact.
All right. After a 10-month, 470 million mile journey, DART is just minutes away from making history. A truly global effort. This mission has brought together people from around the world, united under one goal: to find a way to protect humanity from a hazardous asteroid if one were ever discovered. Now, usually NASA spacecraft are intended to operate for many years or even decades, but not DART. DART was built to be destroyed. DART is a mission of firsts, proving that a spacecraft can autonomously seek, find, and approach a target in space that's so far away we don't even know what it looks like. It also marks the first time humanity will have moved a planetary body in the universe. I said that correctly. Now, at this point, the spacecraft is controlling itself, making small maneuvers to ensure it's lined up with its target. DART is speeding through space and will cover the last 4 miles of its journey in just 1 second. Coming up, we'll hear the final updates from mission operators and witness the big moment live from space. Samson, you have the best seat in the house. How are we looking?
You're right, Hera. Front row tickets to the biggest event in town, and things are looking good. We are T-minus 10 minutes to impact, and DART is precision locked onto Dimorphos and zooming down the home stretch. Now, we have a lot to cover in the time we have left, and I'm thrilled to have with me Lori Glaze, Director of NASA's Planetary Science Division, with me for the ride. Lori, such a pleasure to have you.
Oh my gosh, I am so excited to be here and really happy that we are here in this final 10 minutes. We are almost there.
Well, you were just in the thick of it with the team up until a few minutes ago. What is the atmosphere like in there? I can only imagine.
It's really, it's great. I mean, they're excited. Every time there's a marker that we meet a milestone, everyone is cheering and very excited. But there's also almost a sense of a calm confidence that with every milestone, everything's going, as planned. We're found and we locked on the target as planned, pretty much at the right time. They're looking at the brightness and the reflectivity of the object, and it's more or less what they expected. Everything is performing as expected, and so there's a lot of cheering and happiness, but just kind of a sense, hey, we've been planning for this a long time, and we've got it.
We've got this. We've been planning for this. We can hear applause left and right throughout this evening, all good signs. What are they focused on at this critical juncture, Lori? It is basically years of planning, 10 months of making sure we get to this point after launch, and they've been juggling a lot. Is there anything in particular that they are glued on as we enter this moment of truth?
Yeah, so the main thing they've been watching is getting to that point where we could do the precision lock, where we had good enough signal coming back and enough confidence in where we are relative to Dimorphos that we could really do that precision lock onto the target. And it's hands off now, right? We're not, the spacecraft is going to drive itself, and really focused on that, that point where they could be precision locked. And they're also thinking about looking at and reassessing continuously what's the probability of miss, right? Mm-hmm. As you get closer and closer, that probability should get smaller and smaller, and it is. It looks really, really good right now.
Well, it sounds like the game of thinking, of wondering, really doesn't end until that last second comes to pass. So they can do a lot of great up until this point. We just have to see this through to these last few minutes. Well, and in a few minutes, speaking of that, all the years of thinking, of doing, planning, reacting is finally coming to an end. From 5 minutes to impact, there will be no more opportunity to send any commands to SmartNav in the Mission Operations Center. The team will be purely spectators, the data coming in, and they are just wetting it out like the rest of us for the first time. Lori, this is huge both from an operational perspective and also an emotional one, isn't it?
Yeah, it is. I mean, you can imagine, I'm really excited about it, and I've been engaged with this mission for, the last 4.5 years that I've been in my current role. But this team has been working so hard on this for so many years, and they've put so much of their energy and their time into this, and so much planning and rehearsing, and it's a really big event for them to, like you say, just counting down and watching. At this point, there's not much else they can do but watch and see the fruits of all their work.
Yeah, I've gotten to know many members of this team over the past few months, and there's a lot of alpha individuals on there, right? You need a good mix of alpha people to make sure we get to this point. I can only imagine what they're feeling. Perhaps, like you said, a little bit of relief, a little bit of, can I let this go? I have worked for this one so long, and now we can no longer do anything. That moment is just coming up.
Yeah, but I think they're ready. I think they're at that point. You're getting some shots of Elena Adams, the systems engineer, and you can see the excitement in her voice. She's so ready to show the success of this mission.
This is awesome. 5 minutes out, which we're coming up on now. The team will be hands off 2.5 minutes from impact. SmartNav, which has been guiding the spacecraft autonomously for 4 hours, will also step away, stop any maneuvers. DART will simply be coasting to its fate. This is blockbuster stuff, Lori.
Oh, yeah. Oh, yeah. We are there. Yeah.
I have front row tickets, and we are very soon about to open up these airwaves in the Mission Operations Center. We'll stay plugged in all the way through impact. Remember, at this point, 5 minutes out, no more commands to SmartNav will be possible. The team is watching it just like you and me and the rest of us. All right, we've reached 5 minutes from impact. The final command opportunity to SmartNav has passed, and the team is simply watching that data stream in just like we are. Also remember, there is a 38-second lag for the data to travel to Earth, and also an additional few more seconds for image processing. It's important to note that. should be hearing the chatter in the Mission Operations Center momentarily.
This is DART MSC and DT Mach. 5 minutes till impact. 5 minutes till impact. We are at 1,100 miles away. Also, our window for sending any commands to the spacecraft is done. Contingency's done.
This is a great vibe in that Mission
All right.
Operations Center right now, Lori.
It really is. They are so excited. And
This is investigation
you know,
one on DT
I'm
Mach.
honing in, looking at these images as we get closer and closer, and you look at Didymos, and just you're starting to see this physical body appear there. It's incredible, just incredible.
That sounds great.
I'm still having a hard time believing this is real imagery coming in near real time.
Yeah, but you've been watching it over the last 30, 45 minutes go from just being a collection of individual pixels, and now you can actually see the shape and the shading and texture of Didymos, and we're going to see that same thing with Dimorphos as we get closer and closer. This is so cool.
Never
We're still
before seen
maneuvering.
images of Dimorphos will come into stark relief
Absolutely.
a few seconds before impact. Incredible.
Didymos. It's amazing. All right.
The team is standing, just recognizing this moment, years in the making. It is really nice to see them relax a little bit, get off from those computers that they've been glued to, and just appreciate this moment that's coming.
Yeah, and they've earned this. It's just great to see them there. This is so cool.
Lori, we hit another major milestone. We are now 2.5 minutes from impact, and SmartNav has stopped maneuvering the spacecraft. DART is now coasting toward Dimorphos, and we hope into the history books.
Absolutely. This will be, I'm sure you've heard it many times tonight, humanity's first ever attempt at trying to move another celestial body, and also our first attempt ever to execute a mission in sole purpose of planetary defense. So what an exciting time. Yeah, and I'm starting to see Dimorphos start to come into view there. You can see it starting to take shape. I'm starting to see individual boulders on Didymos. Unbelievable clarity of images
We're
there.
coasting on in. Our projected miss distance is going to be about 17 meters.
All right.
All eyes on this event. Space telescopes, ground telescopes from every continent on Earth.
Yeah.
Yeah.
All right. 2 minutes out.
Does not look like one single rock to me.
Oh, boy, we're getting close.
14,000 miles per hour, Lori.
14,000 miles per hour. And remember, 45 minutes ago, 55 minutes ago, we couldn't even resolve this object in space. And now you can see us zeroing in right on target.
And we're now dropping the clock, and we'll go by loss of signal to confirm impact.
Right. Yes. Imagine we'll get that loss of signal, and then we'll hear from Lena Adams again, and letting us know that we've been successful.
I feel like that'll be a crystal clear signal.
I think so. I think we're starting to see more resolution. In fact, look at that. Didymos has even gone out of the view. We're now just seeing Dimorphos.
This is remarkable stuff.
Oh my goodness, look at that.
Looks like control system settling down. Angular rates look really good. I think we're going to get the investigation team some good pictures.
Wow.
No, come on, we can do better than that.
Starting to see those individual boulders there. You can see shadows of the various rocks on the surface.
Impact. It's amazing, guys. Oh my goodness, look at that. Unbelievable.
Yeah. Looks to me like we're headed straight in. Oh my gosh. Oh wow.
Yeah. Oh my goodness. 8,
Yeah.
7,
Oh,
6,
wow.
5, 4, 3, 2, 1.
Oh my gosh. Oh wow.
Awaiting visual confirmation.
All right. Let's see. We got it? Waiting.
And we have impact. A giant leap for humanity in the name of planetary defense.
Woo. Fantastic. Oh, fantastic. Oh.
What a moment. Very few words can really capture this moment. This is beautiful to watch. Amazing.
What a team. What a team and what an accomplishment.
Team. A few weeks ago, they had their last dress rehearsal. They were getting emotional at the dress rehearsal. They're like, this is crazy. We're getting emotional. This is not the real thing. I can only imagine what they are feeling right now.
Yes. Well, you can see them there on screen. They're all pretty excited. Wow.
Hearing impact, the curtains close on Draco feed. That raw joy from the team, years of hard work and the weight of expectation lifted off their shoulders. This is amazing. This is beautiful. And Lori, really, this is a huge moment for the mission. Lots more work needs to happen in the days, weeks,
Absolutely.
months.
Now, as I always say, it's one of my favorite missions. Now is when the science starts. It just starts now. Now that we've impacted, now we're going to see for real how effective we were. We're going to train all of those ground-based telescopes on the Didymos Dimorphos system, and we're going to make measurements that will help us determine just what its orbit looks like now relative to what it was before. So it's going to be great. Very cool.
All right, this is when science, engineering, and a great purpose, planetary defense, come together, and it makes a magical moment like this.
Yeah,
really.
Absolutely. And you can see so many people there that have made this happen. The team of APL engineers that have really poured their souls into this mission.
Lori, any last words to mark this historic moment?
Oh. We're embarking on a new era of humankind, an era in which we potentially have the capability to protect ourselves from something like a dangerous, hazardous asteroid impact. What an amazing thing. We've never had that capability before.
Thank you so much, Lori. Those are poignant last words. To Hera, history has been made. Back to you.
Wow. I mean, what an exciting day for the DART team. And in case you're keeping score, humanity 1, asteroids 0. Now, I'm here with Nancy Chabot, DART coordination lead. Nancy, talk about a moment to catch on camera. What is going through your head right now?
I mean, I'm just thinking, wow, that was amazing, wasn't it? I mean, those images, you just got closer and closer, and sort of we've been planning for this moment. We've been talking about it for years. At APL here, we've been working on this since 2015, and I knew, I've been talking, this is the images that we're going to see, and they're going to be spectacular. And I think even then they exceeded my expectations of just zooming in like that, and, it really is just such the team accomplishment, and to get to this moment over so many years. And I don't have to talk about it as coming anymore. It's happened now. We have done this.
It's happened, and it is just incredible that as humans, we have done this. We did this. And Nancy, do you have anything you'd like to say to the teams who made tonight possible?
Oh, I mean, I don't need to say anything to the teams because I know everybody like me is really proud to be part of this, right? Proud of this thing that we've been working on for years, and even before 2015, internationally, people wanted to do this. People wanted to take this first test. And then we finally did. Partners across the United States. We have actually 28 countries represented on our investigation team of scientists, telescopes on all 7 continents, everybody doing their part to make this moment happen. I know I'm I'm really honored to be on this team, and I know other people on the team feel the same way.
As you should, Nancy. And I mean, there's a lot to celebrate here tonight. And so now that we have confirmed impact, can you let us know what's next for this mission?
Well, I mean, I think I'm still taking a moment here,
because
this is a big deal. And this was a really hard technology demonstration to hit a small asteroid we've never seen before and do it in such spectacular fashion. But I know other scientists on the team, like me, are already pointing at those images, being like, did you see that boulder? Did you see that smooth area? Did you see the shape? What does that mean? And Lychee Cube is like flying by right about now. They're close approach, taking images, and they're storing them, and we'll get those in the next days. Telescopes here and in space are looking. They're looking at the brightening of the rock that's thrown off from that spectacular collision that we saw. And this is going to go on for weeks. And so there's still a lot of excitement to come, but nothing to take away from this moment.
Yeah, this is just the beginning. It looks like everybody is celebrating here in Mission Operations. I think I just saw Bill Nye there. And so it is a huge day for this team, but also for humanity. You know, Nancy, you mentioned earlier about some of the international collaborations. And could you give us an idea on kind of the scope of DART's mission, right? It's not just us in the United States that's focusing on this. So can you expand a little on that?
Yeah, I mean, planetary defense is really an international issue. We are all on this planet together, right? I mean, and I think it's been so great for this mission to really support and embrace that international cooperation for planetary defense so that we can maximize what we learn. And this idea came about from international scientists talking to each other, working together, you know, in order to make this moment happen for NASA's Planetary Defense Coordination Office, building the spacecraft here at APL. But really, scientists around the world are ready to study the, what did we do to Dimorphos? But more importantly, what does that mean for potentially applying this in the future? I mean, DART really is just the start. It's just the first planetary defense test mission. It was spectacular, and it's accomplished, and we'll figure out how effective it was. That's really what we're going to learn in the next weeks to come. All right, we hit this asteroid. Now, how effective was that at deflecting it, and what would that mean for using it?
Yeah, there's still so much to unpackage here. And so we have a special guest who is wondering, you know, more of what's next for this big mission. So let's hear from her now.
Hey everyone, I'm Danny Hansen, American Paralympic rower and hydro athlete. And first, I would like to congratulate the entire DART team on crossing the finish line. So congratulations. And with that, here's my question. Now that DART has impacted, how will you know if the spacecraft has actually changed the asteroid's orbit?
That's a good question.
Yeah, I mean, so this is a double asteroid system. So all we've done here actually is change slightly how Dimorphos goes around Didymos, right? And the telescopes on the Earth have studied this for years. So we knew it used to be 11 hours and 55 minutes. What is it going to be now? And so the telescopes are going to measure that period change. And they're so good at this. They've done it for decades already to get us to that point. And they're going to work for the next weeks and make that measurement. And when we have it, we're going to be sure to share it with everybody to see how much we did deflect this asteroid with the DART collision.
Wow. Well, Nancy, I mean, it's time for you to celebrate. So congratulations on everything tonight, and go DART.
Oh, go DART. This was spectacular.
Yes. And so we have Samson standing by in Mission Operations with two very special guests. Let's hop over there and see what's going on.
Thanks to Hera. I have the pleasure of introducing NASA Administrator Bill Nelson, who has a special message for us.
Hey, congratulations. Boy, the DART team, you really did this one very well. It's been a successful completion of the first part of the world's first planetary defense test. And there were years of hard work. There was a lot of innovation and creativity that went into this mission. And I believe it's going to teach us how one day to protect our own planet from an incoming asteroid. I really look forward to learning all about what's happening from the observatories so they can tell us about the changes in this asteroid's orbit. So thank you to this international team. We are showing that planetary defense is a global endeavor, and it is very possible to save our planet.
All right.
That was eloquently put, Administrator Nelson. Joining me right now are Deputy NASA Administrator Pam Melroy and APL Director Ralph Semmel. Thank you both for being with me. Pam, I'll start with you. How are you feeling having witnessed this historic event up close?
Oh, I was absolutely elated, especially as we saw the camera getting closer and just realizing all the science that we're going to learn. But the best part was seeing at the end that there was no question there was going to be an impact, and to see the team overjoyed with their success.
That's beautiful. What does this mean for NASA? What does this mean for planetary defense?
Well, NASA works for the benefit of humanity. So for us, it's the ultimate fulfillment of our mission to do something like this, a technology demonstration that, who knows, someday could save our home.
Very powerful. Thank you, Pam. Ralph, you were in that mock for the moment of impact. We've seen a lot of major milestones in APL's history in space. We're talking the first flyby of Pluto, the first mission to orbit Mercury, and now the first spacecraft to impact an asteroid. What was the moment like for you in there?
It was incredible to see how so many years of hard work and creativity resulted in a direct hit of Dimorphos was just an adrenaline rush. I'll add that I've been at the lab now for quite a few years, and I've been involved in a lot of missions and achievements, and never before have I been so excited to see a signal go away and an image to stop.
Ralph, I'm going to give you both a treat right now. We're going to play that replay of impact on our screens right now so we can enjoy it again. Ralph, what does this achievement mean for Johns Hopkins APL? Huge, right?
Oh, it is huge. And in fact, if you'll excuse the pun-like statement here, the impact on APL, as it was on Dimorphos, is immense. This is exactly the kind of mission that APL seeks to do, a never-before-done mission. I'd like to thank NASA for entrusting us with this mission, and I'd like to tell everyone how proud I am of the entire DART team and APL for this game-changing achievement.
Incredible. Thank you, Ralph. And we're watching that replay right now on our screens and just admiring that remarkable achievement once again.
They were just tiny blobs of light, and now they are real objects to us, which is amazing.
Never before seen up until today.
That is amazing. You know, it's just as good the second and third time.
There's that drop-off, knowing we made impact.
Fantastic.
Well, there you have it. A lot of pride here tonight, along with the promise of big things to come. And with a successful DART impact, that will do it for us today at the Mission Operations Center. Back to you, Tahira.
Amazing. I mean, today is a fantastic day. And DART is just the beginning of a global planetary defense effort. In 2024, the European Space Agency's Hera mission will conduct follow-up observations of asteroid Dimorphos and measure in great detail DART's kinetic impactor tests. Let's take a look.
The DART impact is going to be an incredible moment, something we've been looking for over 17 years. My name is Jan Carnelli, and I'm leading the Hera mission for the European Space Agency. The deflection by DART will be measurable from ground with telescopes. However, only with Hera coming up close and inspecting the asteroid will unveil all of those parameters that will allow us to plan for a deflection mission if one day we need one. This is the propulsion module of the Hera spacecraft that will take us to asteroid Dimorphos and will allow us to study the results of the DART impact. The propulsion module is being built here in Italy and then will be sent to Germany, where will be mated with the instruments and the rest of the spacecraft to be ready for launch in October 2024.
We started designing and conceiving the whole mission and the spacecraft about 2 years ago, and we have a launch date to meet that is a fixed date in October 2024. So it's challenging, but we're making it possible. You could say that Hera is really 3 space missions in one. We have one, the main spacecraft that we are currently building at OHB in Germany, but we also have 2 smaller missions that are spacecraft in their own right. Those are the 2 CubeSats, Juventus and Milani.
The CubeSat I'm working on is Milani, which will perform spectral measurements and dust detection following the DART impact. My name is Margherita Cardi from TEVAC International in Italy. We will work alongside the other CubeSat, Juventus, which will perform kind of an X-ray of the asteroid to understand the internal structure.
This is going to be the first time that we have CubeSats on board an ESA spacecraft. Once we arrive there, we will be deploying the CubeSats in order to complement ESA's scientific observations, taking more risk, but also trying to have higher rewards.
The CubeSats will be installed on 2 panels that will be mounted on each side of the structure of Hera. They are just the size of shoebox, however they contain complex technology which will really allow to bring added value to the Hera mission.
Hera and DART represent a fantastic international collaboration between NASA and ESA. The 2 missions complement each other and will validate an asteroid deflection technique that we could use in the future to protect planet Earth.
There you have it. Tonight, we've ushered in a new era in planetary defense. At 7:14 p.m. Eastern, the DART spacecraft targeted and collided with Dimorphos, showcasing a technique that we could use if a hazardous asteroid is ever on a collision course with Earth. Even though impact is over, the process of moving the asteroid is still going on as we speak. Over the next days and weeks, we'll be monitoring Dimorphos from all angles, tracking its change in orbit with ground-based observatories, studying the impact crater and ejected materials with space telescopes, and we may even get images from missions like Lucy, Hubble, and Webb. Now, don't miss a beat. For mission updates, follow Asteroid Watch on Twitter, NASA's Solar System on Twitter and Facebook. Remember, impact was just the beginning. Science and images will be rolling in soon, so stay tuned to nasa.gov/DART. We'll be back at 8 p.m. with members of the team to capture reactions and celebrate this historic event. So join us soon on nasa.gov/live. And for more updates on Artemis and rollback operations happening tonight at the Kennedy Space Center, head to nasa.gov/Artemis-1. Thank you for watching NASA's coverage of DART Impact from Johns Hopkins Applied Physics Laboratory in Maryland. We want to give a special thanks to all of our guests for participating in today's broadcast, and a big shout out to my co-host Samson Rainey for keeping us keyed into the action. Go DART, and good night.
Yo nunca me hubiera imaginado trabajar para NASA. Cuando yo era pequeña yo quería ser cartero, porque me impresionaba la idea de poder caminar por las urbanizaciones y ver las casas de la gente y conocer. Soy Laura Delgado López, soy originalmente de un pueblo que se llama Trujillo Alto, en las afueras de San Juan, Puerto Rico. Llevo casi 3 años en la NASA y soy lo que se llama un analista de política pública en la división de ciencia. Yo trabajo en un campo que se llama política espacial. Y la política espacial tiene que, yo la defino como explicar el porqué y el cómo de las actividades espaciales. Mi trabajo como analista de política pública envuelve asegurarnos que en la agencia estamos siguiendo las políticas, las leyes, las regulaciones que afectan este tipo de actividad, pero que también estamos teniendo un impacto en esas mismas políticas, informando con los últimos descubrimientos que hacen nuestros científicos. Un ejemplo de política espacial que tiene que ver con la política científica y con las actividades científicas, recientemente llegamos a Marte con el rover Mars 2020. Mars 2020 va a recoger unas muestras de la superficie en Marte que puede que nos ayuden a responder preguntas muy importantes sobre si estamos solos en el universo o si ha habido en el pasado vida en Marte. Esa pregunta, aparte de ser fundamental para la humanidad, también impactaría mucho políticas que tienen que ver con, por ejemplo, cómo regresar muestras de otros planetas y de otras partes del universo de una forma segura a la Tierra, de forma que no causen un riesgo. Así que cuando uno piensa en política espacial, hay expertos, ingenieros, científicos, expertos legales, etcétera, expertos en ética, que entonces ven este tipo de actividad y trabajan juntos para definir esas reglas que nos van a proteger en el futuro. Una de las cosas que más me gusta de mi trabajo es como en la división de ciencia va a traer gente que es experto en disciplinas tan variadas y me encanta reunirme con expertos que quizás son los líderes en su campo, en su disciplina. Entonces yo serle útil también y poder explicarle, mira, esto es lo que está pasando en el Congreso, esto es un asunto que se está discutiendo en Casa Blanca, que puede impactar tu programa, etc. A mí me gusta mucho y disfruto esa interacción en la que podemos como compartir lo que ambos sabemos. A los 3 meses de estar trabajando en la agencia, me acuerdo estar caminando, creo que en Nueva York, y ver gente con unas camisas con el logo de NASA. A mí me impresiona tanto que el logo de NASA sea tan famoso. Está por todos lados. Y fue como la primera vez que me sentí reconocida. Yo trabajo allí, me emocionó mucho. Mi familia está bien orgullosa de mí, eso me da mucha felicidad y cada vez que yo puedo compartir cosas como esta, que son en español, me emociona mucho porque sé que puedo compartirlas con ellos. Soy la menor de 3 y mis padres son ambos retirados del sector de psicología. Así que yo creo que lo único que sabía cuando era pequeña era que no iba a ser psicóloga. Aparte de tenerle mucho respeto a la disciplina, yo tengo la dicha de que puedo representarme como yo soy y puedo hablar español y puedo traer mi arte y mi música y todo lo que me apasiona. Y puedo hacerlo de una forma honesta y segura porque las personas con las que me estoy reuniendo hacen lo mismo. Y yo creo que eso al final nos enriquece como agencia y como comunidad. Así que me entusiasma mucho la idea de que esa diversidad va a seguir creciendo y de que voy a estar caminando por los pasillos de la NASA y voy a conocer gente de todas partes del mundo. Los últimos 18 meses han sido tan difíciles en todos aspectos para tanta gente que uno puede encontrar como felicidad y orgullo en cosas bien específicas, personales, profesionales. Yo soy artista, por ejemplo, así que poder hacer mi arte ha sido bien importante en los últimos 18 meses. Así que cuando no estoy trabajando y leyendo sobre política espacial, estoy dibujando. Pero también me siento muy orgullosa de trabajar para la agencia porque siento que nos han cuidado a nosotros los empleados y están tomando decisiones difíciles para protegernos, pero a la misma vez poder permitirnos hacer nuestro trabajo que nos apasiona y que es tan importante. El consejo que le daría a una persona que está interesada en política espacial, primero, que lea mucho sobre el tema. Segundo, es tratar de conocer gente y como involucrarse en la comunidad. Mantener como esa flexibilidad y mantener esa idea de que puedes seguir conociendo gente y aprendiendo sobre carreras nuevas que quizás no habías considerado. Es como una parte bien importante de poder progresar en esta comunidad.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
A critical pre-flight test for Artemis 1, the first trip to space for a NASA astronaut, and new Webb Space Telescope images of neighbors in our solar system. A few of the stories to tell you about this week at NASA. On September 21st, teams at our Kennedy Space Center conducted a cryogenic demonstration test with the Space Launch System, or SLS, rocket for our upcoming uncrewed Artemis 1 flight test around the Moon. The demonstration test was designed to allow teams to confirm the repair of a hydrogen leak that cropped up during a previous launch attempt in early September, evaluate updated procedures for loading the rocket with propellant, and conduct additional evaluations. Keep up with the latest Artemis 1 updates on NASA's Artemis blog at blogs.nasa.gov/Artemis. Also on September 21st, NASA astronaut Frank Rubio launched to the International Space Station from Kazakhstan with 2 other members of the station's Expedition 68 crew. Later that same day, they docked to the station's Rosvet module and were welcomed aboard by the Expedition 67 crew, including NASA's Bob Hines, Kjell Lindgren, and Jessica Watkins. This is Rubio's first spaceflight. Our Webb Space Telescope's first image of Neptune includes the clearest view of Neptune's rings since the images Voyager 2 captured during its 1989 flyby of the distant planet. Webb also captured 7 of Neptune's 14 known moons, including Triton, which orbits Neptune in an unusual retrograde or backward direction. Additional studies by Webb of both Triton and Neptune are planned in the coming year. The Webb Space Telescope recently used its infrared capability to capture its first images and spectra of Mars. Images of the planet's eastern hemisphere captured by Webb's near-infrared camera show surface features such as craters and dust layers, as well as thermal emission, or light given off by the planet as it loses heat. Meanwhile, data from the telescope's first near-infrared spectrum of Mars could give astronomers additional details about the planet's surface and about its atmosphere. That strange noise is what a space rock crashing into Mars sounds like to our InSight lander. InSight detected seismic waves from 4 meteoroid impacts on the red planet in 2020 and 2021. This includes an impact on September 5, 2021, that made these craters. Not only are these the first impacts detected by InSight's seismometer since the spacecraft landed in 2018, but they also mark the first time seismic and acoustic waves from an impact have been detected on Mars. Our DART spacecraft is on track to intentionally crash into the asteroid moonlet Dimorphos on September 26th. The views in this composite image of the Jupiter system were captured during recent testing with the spacecraft's imager and guidance systems to target and track Jupiter's moon Europa as it emerged from behind the planet, similar to how Dimorphos will visually separate from Didymos, the larger asteroid it orbits. DART, the world's first planetary defense test mission, is designed to deflect and alter the course of an asteroid should one ever be discovered that is a threat to Earth. Neither Dimorphos nor Didymos is a threat to Earth. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/Twan.
Scan, the beginning. And we see that communicating to, from, and in space was all NASA, all the time. Our satellites, our infrastructure, our people. Today, some 6 decades later, filling the vacuum of space communications is competition. Commercial industry has come a long way in the past 40 years, and now may reliably deliver most of those same satellite services to space-based users in the near-Earth environment that were once the exclusive domain of NASA. So, NASA Space Communications and Navigation, SCAN, will be investigating viability of the commercial space-based networks to meet the needs of NASA missions flying around Earth. Once demonstrated, NASA intends to move away from government-owned and operated systems and procure commercial comms services. NASA cares about the health of the U.S. satellite industry and will work with everyone to promote industry growth, innovation, and interoperability. By 2030, NASA SCAN expects to migrate from the current paradigm of operating and maintaining government communications systems to a new one, where NASA is just one of many commercial customers in an interoperable near-Earth space, exclusively shopping the commercial marketplace for the best and most cost-effective services to support our closer-to-home NASA missions.
Liftoff of the Falcon 9 and Crew.
NASA expects the space-based market to grow tremendously over the next few decades. Like the successful Commercial Crew program, NASA SCAN will trust its more routine, time-tested tasks to industry innovators and collaborators who'll partner to expand satellite industry norms and standards and embrace interoperability. They'll augment existing processes with autonomous operations and navigation services critical for meeting user needs in a highly congested and dynamic environment. Scientists and mission engineers will seamlessly roam space-based relay and direct-to-Earth communications networks, enabling them to immediately access the freshest data, download the most recent revealing imagery, and, at a moment's notice, nimbly turn satellites and telescopes to cover breaking science, like a volcano erupting unexpectedly or a supernova appearing suddenly in the night sky. All in a user-friendly experience as simple and seamless in space as a call with your smartphone on Earth. And the money NASA SCAN saves in near-Earth orbit will help fund game-changing technologies elsewhere, such as multi-GNSS receivers that work at the moon, multilingual space receivers that can be reconfigured on the fly to communicate and negotiate with any provider for access to their networks, and systems like optical and quantum, literally the waves of the future in NASA deep space communications and navigation. Scan the future, and we see greater efficiency and sharpened focus for NASA. And for our nation and its workforce, a more competitive, innovative, and interoperable space communications industry. NASA Space Communications and Navigation. SCAN. Exploration enabled.
Good evening. I am Ralph Semmel, director of the Johns Hopkins University Applied Physics Laboratory. I am thrilled to be able to announce the successful conclusion of NASA's Double Asteroid Redirection Test, the world's first planetary defense test mission. For the first time, humanity has demonstrated the ability to autonomously target and alter the orbit of a celestial object. The impact of DART into the asteroid Dimorphos was confirmed at 7:14 p.m. Eastern Time when the DART Mission Operations Center here at APL lost signal with the spacecraft. Now, normally, losing signal from a spacecraft is a very bad thing, but in this case, it was the ideal outcome. During the next half hour, we will get a sense of what it was like in the control room as we hear from some of the team members who were there for the final approach and impact of the DART spacecraft. I want to thank NASA for challenging us with this problem and entrusting us with the mission. DART has now joined a long list of APL firsts in space. First photos of Earth from space, creation of satellite navigation with the transit system, the incredible New Horizons flyby of Pluto, and the record-setting Parker Solar Probe that has touched the Sun. We can now add to this list DART, our world's first planetary defense test mission. On behalf of the Applied Physics Laboratory, congratulations to the DART team and to NASA on this historic accomplishment and first demonstration of a game-changing planetary defense capability. Go DART!
Thank you, Director Semmel. And again, welcome to the Johns Hopkins Applied Physics Laboratory, where NASA's DART mission has just made history. I'm Josh Handel with NASA's Office of Communications. Earlier, we saw incredible live coverage of DART's terminal approach with its target asteroid in near real time for humanity's first ever test for planetary defense. Let's take a look at that instant replay and that incredible footage. Wow. So here you can see Didymos and Dimorphos. The spacecraft is autonomously navigating itself. It is precision locked on the asteroid moonlet, cruising in at a speed of 4,000 miles per second. And now you can see Dimorphos slowly filling the screen. We've never seen this object before. Bullseye. We also have incredible high-resolution imagery from DART's Draco camera, which we are now able to show. Here's the asteroid system. Dimorphos filling the field of view. Incredible surface detail of an asteroid 7 million miles from Earth that we have never before seen. Absolutely amazing. Something for the history books. And this is the last frame from the spacecraft before we confirmed loss of signal. I'm joined now by some members from the DART team who have helped turn this incredible first-of-its-kind mission, which honestly sounds like something from a science fiction movie, into science fact. They include Ed Reynolds, DART project manager here at APL, Lena Adams, DART mission systems engineer at APL, Mark Jensenius, DART SmartNav guidance engineer at APL, Carolyn Ernst, DART Draco instrument scientist at APL, and Julie Bellarose, DART navigation lead at APL. At NASA's Jet Propulsion Laboratory. We're going to quickly hear some opening remarks from Ed and Lena, and then we're going to take some questions from our media that we have with us here in the room, both at APL and also dialed into our phone bridge. We're going to try and answer as many questions as we have in the limited amount of time, so let's get started. Ed and Lena, tell us, how are you feeling right now?
Great and relieved.
I'm sure.
So.
Oh, yeah, no, I definitely feel relieved, and it is absolutely wonderful to do something this amazing, and we are so excited to be done.
We've worked on this mission for at least 7 years now, and it's been a work of over 1,000 people that have put their heart and soul into it. So to see it so beautifully concluded today was just an incredible feeling. Right. And also very tiring.
Yeah. Again, a huge congratulations to you and the entire DART team. Absolutely amazing history has been made today. We're now going to take a few questions from the media. For folks in the room with us here, if you have a question, please make your way to one of the microphones in the aisles and state your name and affiliation. And for anyone dialed into our phone bridge, please press *1 to be entered into the queue. Yes.
Hi, Jeff Faust of Space News. So how close of a bullseye was this? I heard something about 17 meters from the center. Do you have an idea of just how close you got to hitting the target?
That's right. We were about 17 meters, getting really close in, and we'll get a much better understanding of where we are from the impact images that the investigation team now is going to analyze for quite some time. Mark?
Yes, so 17 meters was the final estimate out of our onboard guidance. That is to the center of the lit up pixels, so there may be a refinement on that still as the investigation team takes a look at things.
Yeah, because you saw the asteroid was not completely lit from all the sides, so actually finding where that center is going to take some time.
Thank you. We're ready for the next question.
Hi, Joel Achenbach with the Washington Post. First of all, congratulations. Tremendous mission. When did you know you were going to hit it? At what point during the approach did you know this is going to be successful in terms of hitting it, whether it was 17 meters or not, that we're going to hit the asteroid?
So, I'm going to take the first part, and then you can add more detail. But the thing, as we approached, even when we were like an hour or 50 minutes out, it really looked like a nominal trajectory that we practiced over and over and over again. And we practiced all types of different geometries and scenarios. And this was like, I kept telling the people right next to me, this is nominal, this is nominal, this is nominal. So, and it just stayed nominal. So, like 40 minutes out, you were really getting the good feeling. And you could tell everybody in the whole room was getting that same feeling, that it was actually a fairly relaxed environment. It wasn't tense. And then as we hit like the last 2 minutes where we could no longer command the spacecraft, and you knew we were on the trajectory, and you knew that we were not going to do anything to change it, it was just joy. You got to enjoy the moment.
Yeah, absolutely. The one thing I just want to say thank you to the JPL navigation team, because they put us on this perfect trajectory to Didymos. So the way this mission worked is that we were guiding towards Didymos for a while, and then we switched over and started guiding towards Dimorphos. So the JPL team actually did a lot of analysis recently. We executed late maneuvers and were able to put us in the trajectory that basically was hitting bullseye on Didymos. And that is why the whole team felt so comfortable most of the time that we actually were going to impact, and impact well.
You're very welcome.
You're welcome.
Yeah, I'll say that once we got a look at Dimorphos, I think that's when the team was confident that we were going to hit. That was the one unknown going in,
yes,
what
absolutely.
that asteroid looked like. And once we knew what it looked like, we were very confident in the spacecraft's ability to hit it.
Yes, absolutely. That was definitely the defining moment where we were like, oh, yes, Dimorphos exists. Yes. So that was a big relief for everyone. And then, of course, the second part was that we're seeing where we're expecting it to see. It was separating away from the larger asteroid as we expected. And then we were able to execute a textbook maneuver.
Mm-hmm. Thank you. We're ready for the next question.
Hello, thank you. Tarek Malik with Space.com. I think for Elena or whomever would like to do it. You mentioned, or Ed described the feeling as absolute joy. And I'm just curious, I mean, there were a lot of celebrations that we saw actually here. There was screaming and chanting just all the way down. I'm just curious of those last minutes, 5 minutes in, where you were all hands off, what that atmosphere was like. And then what Dimorphos your first thoughts about seeing it up close with those boulders and crags and shadows is like. Thank you.
So I'll say a couple of words, and then I'll give it over to the rest of the team, especially to Carolyn, to talk more about the surface of the Dimorphos. You're welcome. But definitely, as we were getting close to the asteroid, there was a lot of, Ed said joy, I say both terror and joy at the same time, because we saw that we were going to impact. This asteroid was coming into the field of view for the first time. We really had no idea what to expect. We didn't really know the shape of the asteroid, but we knew we were going to hit. So I think all of us were kind of holding our breaths. I'm kind of surprised none of us passed out, actually, for a second there. But at the end, you know, I mean, me personally, I felt a little numb. Like, yes, we were celebrating. There was a lot of joy, but you also feel a little numb that all of this, you know, so many years of work are now complete. Yeah. And so that expectation of what's next is, but there's a lot of next things going on for DART, so I'll let you guys talk about that.
Yeah, I was going to say that these guys, their job is done, but ours is just beginning. So I've been lucky enough to be kind of embedded with the engineering team and watching them all here plan and test and work together. And Draco, of course, was built here at APL, so seeing it come from plans all the way to something that took such amazing pictures was awesome. These guys were all standing up in those last 2 minutes because they were hands off and looking, and I was like this far from my screen looking at the amazing pictures come in because they were just outstanding. And I saw them come in at the same time as everybody here saw them come in, so, you know, we will spend the next months and years doing analysis, of course. Our job has just started, but it really looks just amazing. It's like adorable. It's this little moon. It's so cute. It looks in a lot of ways like some of the other small asteroids we've seen. You know, if you remember, we've seen Bennu and Ryugu recently through NASA and Japanese Space Agency missions, and they are also covered in boulders. So we suspect it is likely to be a rubble pile, kind of loosely consolidated. Didymos, which you saw leaving the frame, I almost wanted to watch it more. You know, obviously we want to hit, but I was like, oh, look at that, so cool. It has maybe craters and boulders and smooth patches, and so there's a lot of work that the proximity working group will be doing over the next few days. We will be finding the exact impact site to really understand, you know, what kind of crater did we make, and of course the ground-based observers are busy as we speak, you know, looking at the data and taking it over the course of the next days and weeks to find out what we really did.
Thank you. We're ready for the next question. Yes.
Hi, Kristen Fisher with CNN. Elena, I was wondering one more time if you could just explain exactly how long it will take before we know if DART was successful in pushing this asteroid off its current orbit. We know the impact was successful tonight. Congratulations. But if you can just walk us through the timing of that second piece one more time. And finally, I'd also like to know if you think that all Earthlings should rest a little easier tonight. Thank you.
Yeah, no problem. Thank you for that question. So we are going to be seeing additional data over the so of course the ground-based observatories are already taking data right now. They're looking at the ejecta. Of course, the JWST and all these other missions are really concentrating on Didymos and Dimorphos. But what we're going to be seeing probably in the next couple of months, we're actually going to get a confirmation of exact period change that we made. So it's not going to be tomorrow, I'm sorry, but it is going, we might see some Lychee Cube CubeSat images coming up in the next day or two, which was the little CubeSat that we let go of about 15 days ago. It should have flown by now and took some images of the plume that we created. So we're going to be seeing that data come down soon in the next couple of days, and then over the next 2 months we're going to see more information from the investigation team on what period change did we actually make, because that's our number 2 goal. Number 1 was hit the asteroid, which we've done, but now number 2 is really measure that period change and characterize how much ejecta we actually put out. And I can't remember the second question.
So just to clarify, you say about 2 months before we know?
Yeah, about 2 months.
Roughly
right?
2 months. My second question was just should...
For the real answer.
Oh, sorry, what was that?
I would say a couple of months for the full quantitative answer.
A couple of months.
Some things will likely come out in even days, maybe weeks, to say this is what such and such a observatory saw, or this is what Lychee Cube saw. I know that they plan to download images the next couple of days. So we'll get some pieces of that answer soon, but I would say the quantitative full answer, a couple months.
And then, Elena, my second
the
question
sleeping
was,
better question.
Should all Earthlings sleep a little easier tonight?
I definitely think that, as far as we can tell, our first planetary defense test was a success, and I think we can clap to that, everyone. I think the Earthlings should sleep better. Definitely I will.
Yeah.
And how do you feel? Like the people working here, we're definitely going to sleep better.
Thank you.
Thank you. Yes. Next question.
Ken Chang, New York Times. Did anything go wrong tonight? I was just wondering, did you have to make any adjustments during the last 4 hours?
No.
We have not.
No.
It's just been wonderful.
This mission was straight down the middle of what our expectations were, and there were no adjustments needed.
No, zero. It was actually kind of disappointing. We prepared these 21 contingencies, and then we did none of them. But we were ready to do them.
You plan them so you don't have to use them.
Exactly. So that's wonderful.
Thank you. Yes.
Hi, Marina Corrin with The Atlantic. Now that you have gotten a good-ish look at the surface of this asteroid, can you tell us in more detail what exactly happened to the spacecraft beyond it was smashed to bits? Like, in graphic detail, like, where are some of the bits and pieces? Are they kind of floating off in space? Are they embedded in this new crater? If you could hover over the asteroid right now, what would you be seeing? Thank you.
Oh, my goodness. That's a good question. I'll let Carolyn take the first
thank you. I would say if you could hover over it right now, there could even still be ejecta coming out because the gravity of this thing is so low that it actually takes quite a while for things to fall back if they do. So you might still see a cloud of ejecta out there for a while.
Yeah. We expect a crater of about 10 to 20 meters, right?
Yeah. So if this is really a rubble pile, it means that it's pretty low in strength, and that means you will get a lot of ejecta. And that means, the spacecraft is kaput, right? We lost signal at the expected times. That clearly broke. You could find some pieces in the crater. You could find pieces. They'd probably be pretty shattered. You could find debris leaving also. So I don't know that you would recognize it. We'll have to see when Hera gets there in 2026 if there's anything left. But my guess is that was such a fast impact that you won't be able to see anything.
And we were also carrying a lot of hydrazine and xenon on board. So we're actually, as engineers, we're discussing in the control room, would we actually see some sort of brightening just based on the fact that we just, evaporate a whole bunch of xenon, too.
Thank you. Yes.
Hi, my name is Maya. I'm here with the NASA Social from Cal State Long Beach. I wanted to ask, can you describe the bittersweet feeling of this DART project that you've been working on for so many years? Do its job and impact the asteroid, but also be destroyed at the same time?
I don't have a bittersweet feeling. We were given a really hard goal, and you focus on the goal, and I don't think any of us named the spacecraft. So, we achieved the requirement, we achieved the goal, and it was we did a methodical process to develop the design that could do that, and it's to me it's more just satisfaction that the process worked and we achieved the goal. And you always think if we missed, the spacecraft lives and we can do, but it's no, we didn't achieve the goal. And so I will relish this moment, and I am happy with the outcome.
Yeah, and I'd like to add that I think the part that we will miss the most as the people who have worked on this for a long period of time is the team. The team we had was amazing, and we really enjoyed working as a team together. We had fun. We built a spacecraft during COVID. We bonded over that, and I feel like that made us stronger going forward. So the bittersweet part will really come in with the fact that the whole team is going to be disbanding now, moving on to different projects, and we all hope that we get to work together again at some point. But the point is that the DART team, as the engineering team and as management team, I think we're kind of done, and we're moving on to other things.
I think the other part of that is like Ed sort of said, this is the goal. This is what it was supposed to do. So we didn't have years and years of it in orbit about something and then it crashed and you remember those good times. Oh, those are great times. You know, the good times were right then. We just saw them. And it was its job. It was supposed to do that to get those good times. So.
Yeah, this was the moment for the spacecraft.
I have to say, I shed a tear when I, at the last image that didn't come out fully. There's a lot of emotion in those critical time, and we had some surprises in the last few weeks and a lot of teamwork going on, and so there's a lot of friendship that's being built. So it was a relief to see that it went so well, and from a navigation perspective, it really went very well, and we were heading straight to Didymos, and we were very happy and relieved that SmartNav didn't have to do that much until it saw Dimorphos. So there's relief, but then at the end, it's just I shed a tear, and it's just the emotion that comes up.
Thank you. We're ready for the next question.
Hi, I'm Brittany Brockington, Upgrade Me Baby on TikTok. My question is, how are you going to go about calculating the new orbit or trajectory of Dimorphos?
I guess I'll take that one. Yeah. So it's all the ground-based observing. They've been observing the system for years before now to get a good baseline as to what was the pre-impact situation. And they'll be observing over the next days and weeks and comparing that to what was there before.
With light curves.
With light curves, yes. So we cannot see the two bodies from the Earth. They just appear almost like a star. It's a point source. But we can tell, much like when you discover an exoplanet, and you can tell that it's there just by the light dimming as it goes in front of the star. It's similar for the Didymos system. So you get eclipses between the main and the moon. And so you're measuring the timing of those eclipses, and that's what tells you how shortened the orbit got.
Thank you. Yes.
Yeah, Isam Ahmed from AFP. Just to piggyback on a colleague's question for Carolyn, you mentioned it looked cute to you. Were there any sort of other adjectives that came to mind? What would you describe its shape as? For me, it looked like either a bread bun or an egg. What sort of thoughts came to your mind?
Yeah, every asteroid is a potato, right? Yeah. I mean, and it's amazing, right? It is awfully egg-shaped, though. Compared to other things that we've seen, that moon looked very, not ellipsoidal quite, but, like egg-shaped with a bunch of boulders clearly on the top, like it's a pile of rubble. I was actually a little surprised by the shape of Didymos, too. We had a radar model, which was good, and it got the bulk shape, but it actually was more elongated than I thought. And, of course, you cannot see details with that radar model that we have, and so you could start to see, I think that's a boulder. Oh, you can see it. Oh, it's a crater. Oh my gosh, is that a smooth patch? That's amazing. So we're going to be able to tell a lot about how the system formed and what it has experienced over time as we look at these images closer.
Thank you.
Thank you. I believe we now have a question from one of our reporters dialed in.
Hi, yes, these are the questions from the phone bridge. I do have two. The first is from Stephen Clark at Spaceflight Now. He's looking to know if we have confirmation from Listia Cube in terms of taking any photos, taking any pictures, and what would be the earliest opportunity for a downlink and seeing those. That's the first question, and I'll have one more after that.
We're trying to get a pass 3 hours from now. Okay. So we did, 40 minutes before impact, we did get a short email from our Italian colleagues, and they were shooting to get an extended pass about 3 hours from now, and that would be the very first opportunity. And so it's just a matter of, can the DSN schedule the pass, and can they just coordinate, in addition to other telemetry, getting the image down. But it is a priority for them. Okay.
Great, thank you. One other question from the phone bridge for now. Jim Siegel with NASA Tech. The question is that he understands that JPL keeps a Sentry risk table of objects, and are there other asteroids or other objects that have already been identified to go after next?
So I can jump in here. Yeah, for any questions related to any future planetary defense efforts, please reach out to NASA's Office of Communications for response. Thank you. Next question.
Hi, I'm Gretel Benischek, and I attended the NASA Social, and I'm a student at Embry-Riddle. My question is, an asteroid hit Mars last Friday, I think, and I just didn't know if that was when we say that's planetary defense, is it just Earth? At this point, I mean, I know it's really premature to ask that, but I just when I read that last week, I was like,
there's stuff everywhere. Every planet gets hit, the moon gets hit, everything else. Asteroids get hit, not just by DART, all the time, and we often use those craters to tell us more about what happened in history. A lot of that history on Earth is gone. And so we can look at those other planets, the moon and other planets around us to know like what happened in the beginning to get us to where we are now. But oh my gosh, there's a lot of craters there. So a lot of stuff happened, but now not so much. A lot of time has gone by. But in terms of defense, we're the only place with life right now, right? So that's what we're really primarily worried about.
Yeah, but Planetary Defense Office does actually look at all of these impacts and really assesses what happens. And that's part of the Planetary Defense Office